you can have, just like you can have for limits, you can have one-sided limits, right? We found that if you had a function that went like that and then it started like this, remember we talked about you can have two-sided limits. Like if you come from the left side of this point here, okay, if you come from this side, the limit looks like it's whatever that value is, but if you come from this side, the limit looks like it's whatever that is. The two limits are different on either side. It's going to be the same thing with derivatives. You can have one and two-sided derivatives. You can talk about the derivatives at a point not being the same from the left and the right. So the function that I'm giving you is this one to look at graphically first. On the left-hand side, you have x squared, so you have half a parabola. I'll exaggerate it at the bottom there. And then on the right-hand side, you have this steeper line like that. So what we're looking at is the fact that the derivative from one side is not going to be the same as the derivative from the other side. The right-hand derivative is if you're finding the slope by putting a point on there and one point on the right. From that, actually, you can tell me what the slope is because it's the same everywhere. If I draw a line where I'm going to the right, what's the slope of that line, even though it should be right on top of the other one? What should it be? It should be 2. It is 2, right? The right-hand derivative is 2. What should the left-hand derivative be? If I was to have that point get closer and closer and closer, what would happen there? What's the slope going to be if I push this point closer and closer? I know these drawings are spectacular, but why don't I show you this instead? The right-hand derivative is if you put that point right on there, and then, whoops, I have to get rid of that. Do the secant line on the right. If I set up my derivative expression, but then move this point closer and closer, the slope is 2, right? And in fact, the right-hand derivative is 2, right? Because the slope anywhere here is 2. Anywhere you put that point. If you put the slope on the other side, the slope from the left-hand side, if you make this point get closer and closer and closer, what's that slope approaching? 0, right? So the slope from one side is, the slope from this side is 0. As you get closer and closer, the derivative is 0. On the other side, the slope is always 2. So at that point, at the bottom there, they're not the same, right? The derivative from the right is 2. The derivative from the left is 0. At that point, it is not differentiable. You can't say what the derivative is at that point because the left and the right are different. Right? Because the limit, the derivative would be, the definition of the derivative would be limit as h approaches 0 of f of x plus h minus f of x over h. But if that limit doesn't exist because the limit from the right and the left are different, this thing is who knows what, right? Because the left and the right are different here. The right-hand derivative is just the generic definition here, basically what I just have there. But 0 from the plus side. Let's make that a different color so it stands out. Doesn't stand out that much, I guess, but let's make it stand out this way. That's a little too big. That would be a little excessive. This is probably enough here. Plus. How about that? 0 from the plus side. Should do them this big, right? Not good. The other side from it's just the left-hand limit or the right-hand limit, right? No, you want that? That's better. A little too excessive otherwise. Okay, that's the generic definition, but basically the only difference is you're coming from the left or the right. I would like you to find the left and the right hand. We already see what they should be, right? The right-hand derivative should be 2. The left-hand derivative should be, I guess I should at least abbreviate a little bit there. The the left-hand derivative should be 0. We've seen it graphically, but I want you to work it out algebraically now. The left-hand one is easier to do than the right-hand one. Left-hand derivative, I want you to work it out using the definition. And then I want you to work out the right-hand derivative using the definition. The right-hand derivative is a little bit more tricky because you got to think about which function applies at the point and which function applies to the right or left of the point. Notice how this is defined. At 0 and to the left of 0, this function applies. And then to the other side of 0, this function applies. Okay, we'll pause this while you try that. Before you get too far with this, make sure you've set it up properly. You have to think about which function applies at any given point here. If h is approaching 0 from the negative side, it's less than 0. H is negative in this case, right? It means that you're looking at from the, like if h is negative, it means this value is a negative value, right? So which of the two functions applies when you're on that side? When you're on the left side of 0, which of the two functions apply? This one, right? And when you're at 0 itself, which one applies? This one. That one applies to both of them. If we want the derivative at 0, notice you can't, like I wrote this expression, but really it's got to be, it should be thinking of this value here, right? We're looking at 0 plus h minus f of 0, right? You can't talk about the left and right-hand derivatives in general. So really I should be putting in here 0, 0, right? Because that's the specific point. If you do that, then you said that the function that applies here is that squared, right? And this squared. If you work this out, minus 0 squared. It'll work the other way as well, even if you do it in a generic way first, but 0 plus h, if you multiply that whole thing out here, 0 plus h, I'm going to write it out this way and say 0 squared plus 2 times 0 times h plus h squared minus 0 squared. I know that's good, eh? What do I end up with there? I end up with, all of this cancels out. I end up with 2 times 0, or in other words 0 plus h. Right, the limit of that. If you work all that out, it's going to pretty much end up being 0. We know that, right? This is the easier one. When you sub in now 0 for h, you get 2 times 0 plus 0. I could have gotten rid of the 0, the other part before, right? I could have just said that whole thing's gone, and I could have said I got h squared over h if you really wanted to. Right, I could have canceled that out before, and in fact I probably should have, because you don't really need it down the road here. Limit of h, if h is 0, it's 0. Okay, that's 0. On the other side, though, you have to think about what function applies here. On the other side, when we're talking about, and let's put the right numbers in here first of all here so we can see what we're looking at. We have 0 plus h and 0. But we're on the right side now, right? This time you're on the right side. So h is a positive number. Which function applies here when you're on the right side of 0? This one does, right? So we have limit as h approaches 0 of, I got to do this function, 2 times 0 plus h, right? 2 times 0 plus h. Do you see why you use that function? When you're above 0, you got to use that function. What function has to go here, though? At 0 itself, that x squared function has to go there, right? So this is 0 squared. Okay, you need to use a different function. One of them is 2 times the function. One of them is the function squared, because the two are different. And at 0, one of them applies. Above 0, the other one applies. That's why that's different. This is tough to analytically get it to work out to what you want it to show this. It's only because you're working from one side of 0. This gives you what here? you have 0 plus 2h minus 0. I guess you don't really need those, right? Or in other words, you have 2h over h. Are you okay with where that comes from? And so that's where the 2 is going to come from. 2. That's how you get the 2 there. Technically, at 0, this function applies, x squared, right? That's why you have 2 different functions in this step. That seems to be the most troubling thing. This is not a huge deal, this 1 and 2-sided derivatives, but we should make sure we're okay with it. Yep. Questions about this? Because if you look at how it's defined here, if you think about the graph, right? Graph looks like that and goes up here. One of the points is on the right side in our definition, right? This one? No, not that one. This one? This one's to the right. It's up there. That's on this line, right? That's on this thing? Because up there it's the line, right? But at 0, this is the function that applies. It says less than or equal to 0. That's why those are different there. Because of the way the function's defined to begin with. That's it for that first section. I put some kind of a summary in here if you happen to like that kind of stuff. That's the definition of the derivative. Remember that when you're talking about a point, there was this alternate definition you could use. There was a bunch of different notation for the derivative, and then right and left hand just has to do with, the only difference for right and left hand is that, right? Whether you're approaching from one side, the one-sided limit. We have started looking at graphing derivatives from the function and the function from the derivative. But we'll continue to do that as we work through the next couple of units, because that's a tough thing to do. Are we okay? We're going to talk about the first part of the next section before calling it a day.